In the next example problem, we have a sled that's being dragged across the ground, and we are told that the sled is dragged across the ground at constant speed. There is a force of tension pulling the sled, there's a force of friction opposing the sled's motion, and as in many problems, we have gravity and the normal force. The first part of this question asks us to find what is the tension in the rope. So the tension force itself is pointed 20 degrees above the horizontal, but we just want the total magnitude or the total strength of the tension force. And the thing that will allow us to calculate this is this phrase right here, constant speed. Constant speed immediately tells us that the acceleration of the sled is going to be 0. And if the acceleration is 0, that is essentially giving us two pieces of information. The acceleration in the x direction is 0, and the acceleration in the y direction is 0. One example of 0 acceleration is an object that is stationary and not moving at all. But this is not the only possible example of 0 acceleration. An object that is moving at a constant speed and not changing its direction of travel, that is an object with constant velocity, basically what we have in this scenario. And if your velocity is constant, that means your acceleration is 0. So in this problem, we are going to solve part A. This could effectively have been a chapter 4 question on forces. If you have an object moving at constant speed, you know something about the coefficient of friction, the other forces acting on the object, the angles. Can you determine what some properties of the unknown forces are? So to answer this question, we are going to write down every force and in its components as much as possible. So for the x components of the forces, we could say the x component of the normal force is equal to 0. The x component of the gravity force is also going to be equal to 0. I do not know what the x component of the force of friction is, but I can say that the force of friction in the x direction will be equal to negative mu times whatever the normal force is in terms of the total strength of the normal force. Now, we do know what mu is in this problem. The coefficient of friction between the sled and the ground is 0.5. So if I want, I could write this as negative 0.5 F normal. And the tension force, this is really the thing that we want. I do not know what the strength of the tension force itself is, but I can write the force of tension in the x direction as the total strength of the tension force times the cosine of 20 degrees. And we also do know the acceleration in the x direction. Because our object is moving with a constant velocity, I can say ax is equal to 0. Now, very similarly, I can write out all the forces in the acceleration of their y components. So I could say the y components of all the vectors drawn on this picture, F normal in the y direction. I do not know what the normal force is. It will not be the same as the force of gravity because gravity is pulling it down, but the tension force is kind of pulling it up. The normal force is pulling the sled up, and all three of these forces have to cancel in the vertical. So I expect the strength of the normal force plus the vertical component of the tension force will cancel with the force of gravity. For now, I do not know what the strength of this normal force is, so I'll just call it Fn for normal force. The normal force is entirely in the y direction. It has no x component at all. Now, the strength of the gravity force, I can write something for that. The force of gravity in the y direction could be written as negative 18 times 9.8 18 for the mass of the sled with the bricks on it, and 9.8 the acceleration due to gravity. I have a negative sign here because gravity is pulling it downward. And when I put that in a calculator, I find that the strength of the gravitational force is going to be 176.4. So I get negative 176.4. For the force of friction, there is no friction force in the vertical direction. The force of friction is entirely in the horizontal direction. So I could write the force of friction in the y direction will be 0. And for the force of tension in the y direction, well, tension force itself will have a horizontal component that we accounted for over here, and the force of tension will have a vertical component. So I can write the force of tension in the y direction is going to be the total magnitude of the tension force. The total magnitude of the tension force is whatever this total magnitude of that vector is. I am calling it Ft. So I can write this as Ft sine 20. And then again, we were told that constant velocity implies 0 acceleration. So I could write Ay is equal to 0. Now, if I look at all these terms, notice I only have a number for one of these terms, and that is the force of gravity in the y direction. Plus all these other terms there are 0, but I'm not counting that. I don't know the normal force. I don't know the tension force. But here and here I have normal and tension force. Here I have a normal force. Here I have a tension force. In total, I only have 2 unknowns written on the board right now. At this point, we rewrote everything just to make it a little bit neater. If I wanted to, I could go to a calculator, type in cosine 20 and sine of 20 for the horizontal and vertical components of the tension force respectively. Cosine of 20 is 0.94, so I could write the horizontal or the x component of the tension force as 0.94 times the total strength of the tension force. And I could write the vertical component of the tension force as 0.34 times the total strength of the tension force. So now we're going to set up Newton's second law twice, one for all the horizontal components of the vectors, one for all the vertical components of the vectors. So if I set up f net x equals max, on the left-hand side of Newton's second law, I have the horizontal component of all the forces. That are these 4 terms here I have to add together. So I get 0 plus 0 plus negative 0.5 Fn, so minus 0.5 Fn, plus 0.94 Ft, so plus 0.94 Ft. And I added up all the horizontal components of all the forces equals max. Even though the mass of the sled is 18, it doesn't matter because ax is 0 anyway. So I could set this all equal to 0. I could do the exact same thing for the vertical components of all these forces. If I write F net y equals may. Now when I add the vertical component of all of these forces together, I'll have plus F normal minus the force of gravity in the y direction. So I'll have F normal minus 176.4 plus 0. Friction has a vertical component of 0 plus 0.34 F tension plus 0.34 F tension. And just like before, AY is 0, so equals mass of the bricks times 0. It doesn't matter, so I could set all this equal to 0. To answer part A of this problem now, we just have 2 equations with 2 unknowns. This is a system of equations. The rest of this problem is just algebra. So let's take this equation and let's rewrite it as F normal is equal to 176.4 minus 0.34 ft. All I did was I brought everything in this equation to the right-hand side except for F normal. Now I am going to take this result for the normal force and plug it in right here. And when I do that, I get that negative 0.5 times all this stuff times 176.4 minus 0.34 ft plus 0.94 ft, and that is all going to be equal to 0. Now I have one equation with one unknown. This problem is solvable. And when I go through the arithmetic of this problem, I find that the tension force, after a couple lines of work, F tension is 79.5 newtons. We're now asked to find the work done by the tension force when the sled undergoes a displacement of 20 meters. So to answer that question, we said that the work done by a particular force acting on an object is given as the strength of that force, the magnitude of that force in other words, times the displacement of the object, or the distance that the object travels, times the cosine of the angle between the direction that the object travels and the direction of the force we're considering. Now, in this particular question, we are asked about the tension force. So if I'm asking about the work done by tension, I'll have the force of tension be my force here. And this angle is going to be the angle between the direction that the sled travels and the direction of the tension force. So the work done by tension could be written as the strength of the tension force, that is the magnitude only. So that would be 79.5 newtons. The distance that the object travels, in this particular example, we're considering the sled to have traveled 20 meters. And the angle between the displacement vector and the force vector. In this picture, the displacement vector is in the positive x direction. The force of tension is 20 degrees above the positive x-axis, 20 degrees above the horizontal. So here I would have cosine of 20. At this point, I have numbers for everything, so I could plug these numbers into a calculator and find the work done by the tension force is going to be 1490 joules. So the rope, the pull of the rope, the force of tension will give 1490 joules of energy to the sled when the sled is dragged for a distance of 20 meters. Part C of this problem asks us to find the work done on the sled by the force of friction when the sled is dragged through a displacement of 20 meters. Now, hypothetically, if we wanted to, we could go back to the earlier parts of the problem. Now that we know the tension force, we could use that Ft to find the normal force acting on the sled. If we know the normal force, we could then find the force of friction acting on the sled. And if we know the force of friction acting on the sled, we know their relative directions compared to the displacement, and use that to find the work done by friction acting on the sled. But I want to claim that we do not need to go through all of these steps. I claim that it is possible to determine the work done on the sled by the force of friction without having to do any calculation at all. This is something we could just do in our heads. So if you want, pause the video, think about what we've talked about so far in this chapter, and see if you could figure out how we could determine the work done by friction on the sled without having to do any calculation on paper. So how do we do it? think to the work kinetic energy theorem. The work kinetic energy theorem tells us that the total work done on an object, the net work done, the work done by all the forces, has to add up to the change in the kinetic energy of an object. So let's look at the net work done on the sled. In this problem, there are 4 forces acting on the sled. So each force will contribute to the work done on the sled in some manner. I have the work done by the tension force acting on the sled. I have the work done by the force of friction acting on the sled. I have the work done by the gravitational force acting on the sled. Plus I have the work done by the normal force acting on the sled. And all of these works have to add up to the total change in kinetic energy of the sled. So equals delta KE. Now, if I look at the work kinetic energy theorem for this particular problem, I remember that the sled is moving at constant speed throughout this entire experiment. So if the sled is moving at constant speed, final speed and initial speed are the same thing. That tells me that my change in kinetic energy is going to be 0. So this delta KE is going to be 0 for this particular case. The sled is not speeding up or slowing down. Also, if I remember what we talked about before, whenever I use the equation for work, we said work is equal to FD cosine of theta. And if theta is 90 degrees, it doesn't matter how strong the force is, the work is still going to be 0 because the cosine of 90 degrees is 0. So whenever the force is perpendicular to the displacement vector, that force will contribute 0 work. So in this case, the force of gravity is 90 degrees away from the displacement vector. So the work done by gravity will have a cosine of 90 here. That will mean the work done by gravity is just going to be 0. And by the exact same reasoning, normal force points straight upward, displacement is to the right. The normal force and the displacement are offset by 90 degrees. The normal force will do 0 work on the sled. So let's look at what we're left with. The work done by the tension force we found earlier, that is 1490. The work done by friction, that's what we want. So I'm going to just write work done by friction. And then I get plus 0, and that is equal to the change in kinetic energy. But the sled did not speed up or slow down. The sled never changed its kinetic energy. The change in kinetic energy is 0. And right away, I can look at this equation and see that the work done by friction on the sled is going to be negative 1490 joules. As I said, hypothetically, if we wanted, we could go back to the start of the problem, find the normal force, use that to find the strength of the friction force, use that to find the work done by friction. But this is a lot easier to do. As I said earlier, very often the work kinetic energy theorem can be a very powerful tool for solving some problems, and it can let you solve some problems very quickly in this chapter.